All right, before we can even think about tackling something as huge as string theory, we've got to get our heads around the world it's built on. And that world is quantum theory. So I need you to just forget everything your gut tells you about how reality should work, because quantum mechanics, that's the actual rule book for the universe. And let me tell you, the rules are weird, they're fascinating, and they are absolutely fundamental.
So, what are the fundamental rules of reality? I mean, that's the big question, right? For hundreds of years, we thought we had it all figured out with Isaac Newton. His laws were beautiful, they were elegant, and they described everything from an apple falling from a tree to planets orbiting the sun. But right around the turn of the 20th century, scientists started looking at really, really small stuff. And Newton's perfect rules didn't just bend, they completely fell apart.
And that brings us to our first major clue that something was deeply wrong with the old way of thinking. This was a puzzle so big, so profound, they literally called it a catastrophe for physics. I know, it sounds totally nuts, but this was a genuine crisis. Picture a hot oven. The physics of the time, classical physics, predicted that as it heats up, the energy waves inside should just keep getting smaller and piling up until you have an infinite amount of energy, especially in the high-energy ultraviolet part of the spectrum. I mean, theoretically, this meant that turning on your oven should unleash a blast of deadly radiation and light that would vaporize you instantly. But, it obviously doesn't.
And yeah, that massive, glaring failure became known as the ultraviolet catastrophe. It was this huge red flag, basically screaming that the old theories were completely wrong about how energy and light actually work. The math predicted total disaster, but thankfully, reality had other plans. So, how on earth did they fix this? Well, in 1900, a physicist named Max Planck came along with a truly radical idea. He said, what if energy isn't some smooth, continuous flow, like water coming out of a tap? What if it only comes in tiny, individual, discrete packets? I mean, this was a wild, counterintuitive guess, but it was about to change everything. Planck called these little energy packets quanta. And by assuming that energy could only exist in these fixed amounts, like currency only coming in pennies, dimes, and quarters, his math suddenly worked. It worked perfectly. It totally prevented that infinite energy problem at high frequencies. And just like that, the ultraviolet catastrophe was solved, and the quantum revolution had officially kicked off.
Okay, so Planck's idea was a bombshell, but it really took another genius to pick up the ball and run with it. And that brings us to our next section, where we see how Albert Einstein used this brand new idea of quanta to solve a completely different mystery. So this new mystery was called the photoelectric effect. On the surface, it sounds pretty simple. You shine a light on a piece of metal and poof, it knocks some electrons loose, creating an electrical current. This is actually the basic idea behind how solar panels work. But when scientists looked closer, the details were just baffling. Okay, now here's where it gets totally backwards. Common sense and old school physics would tell you that a brighter light is like a more powerful wave, right? So it should hit those electrons harder and send them flying off faster. But that's not what happened. Experiments showed that a brighter light just knocked out more electrons, but didn't make them any faster. And even weirder, if you used a low-frequency light, like red light, it didn't matter how bright you made it, nothing happened. Not a single electron would budge. And then Einstein comes along and connects the dots. He proposed that light itself isn't a continuous wave, but is actually made of Planck's little energy packets. He gave them a name, photons. Each photon carries a specific punch of energy that depends on its frequency. So it's like a game of billiards. One photon hits one electron. A brighter light just means you're shooting more photons, so you knock out more electrons. But if you want to knock an electron out faster, you need a single photon with more energy, which means a higher frequency light. It was just a stunningly simple and elegant solution, and it's the work that actually won him the Nobel Prize.
So light is a particle, a photon. Case closed, right? Well, no. Not even close, because light is also a wave. And this is where things get truly, deeply strange. Welcome to the idea of wave-particle duality, one of the absolute cornerstones of the quantum world.
To really see this duality in action, we have to talk about what is probably the most famous, most mind-bending experiment in all of science, the double-slit experiment. The setup is almost ridiculously simple, but I promise you, the results will challenge everything you think you know about how reality works.
So imagine you shine a beam of light through two tiny parallel slits. Now, you might expect to just see two bright lines on the screen behind them, but that's not what you get.
Instead, you see this weird pattern of many alternating bright and dark stripes. This is a classic interference pattern. It's exactly what happens when water waves go through two openings and ripple into each other. The peaks add up to make bigger waves, and peaks meet troughs and cancel each other out. Makes perfect sense for our waves. Okay, fine, light acts like a wave, but what if we try this experiment with something that we know is a particle? Like a tiny little bullet called an electron. You'd expect them to just fly through the slits and hit the screen in two distinct lines behind each slit, right? I mean, that's just common sense. But here's the part that is just absolutely mind-blowing. When physicists actually did this experiment with electrons, even firing them one at a time, they still got an interference pattern. Now let that sink in for a second. A single particle, the electron, leaves the gun, and somehow it behaves as if it went through both slits at the same time and interfered with itself. This is the absolute heart of quantum weirdness. So what does this all mean? It leads us to this core concept of wave-particle duality. In the quantum world, things aren't just particles or waves. They're somehow, mysteriously, both at once. Which property you end up seeing just depends on how you measure it. And this isn't some quirky little side effect. It's a fundamental truth about reality itself. And any deeper theory, like string theory, has to account for it. And you'd think the weirdness would stop there. But nope. As if that wasn't strange enough, quantum mechanics also tells us there's a fundamental limit to what we can even know about the universe. There's an unavoidable fuzziness baked into reality. This is Werner Heisenberg's famous uncertainty principle. And what it reveals is a fundamental trade-off built right into the fabric of reality. The more precisely you nail down a particle's position, the less you can possibly know about its momentum, how fast and in what direction it's going, and vice versa. The more you know its momentum, the fuzzier its location becomes. And crucially, this isn't because our measuring tools are clumsy. It's a hard-coded rule of the universe. It's just the way things are. So, we've got a universe where reality has a built-in fuzziness. What happens when we take that idea and the idea of quanta and we push them to their absolute logical extreme? If energy comes in chunks, could space and time be chunky too? Are there pixels to reality? Well, it sure looks like the answer is yes. Let's start with space. I mean, it seems perfectly smooth and continuous, doesn't it? But is there a smallest possible unit of distance, a fundamental pixel of space? The answer seems to be yes. It's a distance known as the Planck length, and it is just unimaginably tiny. This number right here represents the absolute limit. Below this scale, our concepts of space and distance just completely break down and stop making sense. And if space is pixelated, you guessed it, so is time. It also has a fundamental, indivisible unit called the Planck time. This is the shortest possible tick of the cosmic clock. It's the amount of time it takes light to travel just one Planck length. You cannot have a moment shorter than this. Okay, so let's try to wrap our heads around this. We've got the Planck length and the Planck time, the smallest pixels of reality. But things get really wild when we look at Planck mass and Planck energy. Now, the Planck mass itself isn't that tiny. It's about the same mass as a large bacterium. But here's the mind-bending part. Imagine squeezing that mass into a space the size of the Planck length. The energy that creates is just staggering. It's like packing the explosive power of a ton of dynamite into a space smaller than a single proton. This is the extreme scale where gravity and quantum mechanics have to finally merge, and it's exactly the sandbox where theories like string theory have to play. And I really have to stress this. These Planck units are not just a mathematical party trick. They are the natural result you get when you combine quantum mechanics with Einstein's theory of general relativity. They are a huge clue telling us that at its most fundamental level, space-time itself is granular. It's pixelated. There really is a smallest unit of space and a shortest tick of time, all flowing directly from the bizarre quantum rules we've just been talking about. So here we are. We're left with a universe built on tiny packets of energy, where things can be particles and waves at the exact same time, where there are hard limits on what we can ever know, and where the very fabric of space and time is pixelated. This is the strange, beautiful, and utterly baffling world of quantum mechanics. Which leaves us with the final question to think about. If this is the foundation, what kind of reality does a theory like string theory, which has to explain all of this, actually build?